In Chapter 11, we meet two new ideas that are both very important. One is the idea of momentum, which is mass times the velocity vector. So note that momentum itself is a vector. You can work with it in components just as you would the velocity vector. Impulse has two definitions that are equivalent, and you'll use each one depending on the situation, possibly both. One definition of one definition of impulse is that it's the time integral of a force. And the reason you would do this is because you might have a force that is not constant in time, that the force is in fact changing in time. And typically we're going to use this in the scenario of collisions, where you have a very large force over a very small period of time, such that you can use what's called the impulse approximation and consider all other forces negligible over this short period of delta t. So doing this integral over time tells you your impulse, and impulse is also defined as the change in momentum. Hence, we can relate these sudden large forces to be a change in momentum. One of the big applications of this is the idea of collisions. There are two main collision models that we use, and note that these are models. One is the idea of a perfectly inelastic collision in which two objects stick together such that their final velocity is the same. A second one is a perfectly elastic collision in which they bounce apart. In this case, mechanical energy is conserved. In both of these situations, momentum is conserved. We in fact would say that momentum is conserved for any isolated system. If you have an external force acting on your system, then momentum changes, but as long as you've considered all of the pieces to be within your system such that it's isolated, momentum is always conserved, where that would be total system momentum. Another example of something that's similar to collisions but a little bit different is the idea of an explosion. And in this case, you're starting with one piece, typically, which breaks into multiple pieces, two or more, and we would say that the total momentum is conserved. So if you do this in the reference frame where your object is initially at rest, if this occurs in 2 dimensions, you would say that your total momentum in x is 0, your total momentum is in y is 0, where you've summed up the momentum of each of these 3 pieces. So there's an important model that actually has 2 different models within it, and this is our collision model. It's important that you distinguish whether you're applying the inelastic collision model or the elastic collision model. And in this case, there would be 2 objects, and they would be colliding in a straight line such that we don't need to consider what's happening in 2 dimensions. This is one-dimensional. In this case, in the inelastic collision, we say that the final velocity is shared, but their initial velocities are separate. In the elastic collision, the definition is that there's no loss of energy. The equations that we have for this are only valid if object 2 is at rest. These equations have been derived using conservation of momentum and conservation of energy, assuming that object 2 is initially at rest. If both objects are moving, then one approach is to use the Galilean transformations, which is just transforming the reference frame so that object 2 is rest. You do your calculation, and then you transform it back. So these models are valid in these 2 scenarios. There is a case in between, and we don't have a model for that. We would actually need to consider the details of what's occurring a little more in detail. So our general problem-solving strategy whenever you're dealing with conservation of momentum is to first define your system. Momentum is only going to be conserved if your system is isolated, which means that there's no external forces, or if we can use what's called the impulse approximation, which assumes that all forces are much smaller compared to the interaction force that we're thinking about, like the ball bouncing off the wall. We could ignore gravity during that bounce. If we can't actually define the isolated system, hopefully you can define part of the system to be isolated. And so always make sure that you're going through this step and being very careful with it. The visualization that we use for this is a before and after representation, just like in energy. And one thing to be careful about is that notationally we use capital P for total system momentum, and we use lowercase p for momentum of individual objects, being very careful with your subscripts to distinguish between final and initial. We use numerical subscripts to usually distinguish between different objects, and then we would use x and y to work in multiple dimensions. Frequently, you only need to work in one dimension.